All right, in this section we're going to talk about MOSFET scaling. So first, why do we want to do this? The idea is you have a certain amount of real estate on a silicon wafer, and the more of these little MOSFETs you can put on it, the complexity of your chips can go up, and also your profits can go up because you can make a larger number of more complex chips for the same amount of real estate. You also get some benefits in terms of the speed at which you can run these devices, or the frequency. There are some downsides though, and these come from the physics of the devices themselves. So under this general heading of MOSFET scaling, we're going to think about taking a MOSFET and shrinking the parameters, the physical parameters, such as the channel length L, down to some smaller length K times L, where K is some number less than 1. So when you do that, we have to look at all the other things that change because the channel length shrank. So typically when you shrink the channel, you'd also want to shrink the gate oxide thickness. So the T oxide goes to K times T oxide, etc. So all of these different changes are going to influence the threshold voltage and all of the other performance parameters of this device. There's different ways that you can do the engineering design within this idea of scaling. So the way I like to think about this is sort of a staff meeting amongst engineers, and some of the engineers say, when we do this scaling, we want to keep all our voltages constant. And then some of the device physicists say, when we do this scaling, we really want the physics of the device to be as close as possible to the last generation because we knew how it worked, and therefore we want to keep the E fields constant. So you can write scaling laws in terms of constant voltage or constant E field or some mixture, sometimes called general scaling. So which one a certain company chooses to do is going to be set by that debate in the staff meeting amongst all the engineers. So if L goes to K times L in each of these, in the constant E field scaling, you would keep the voltage drop across the depletion width in the semiconductor constant, so that you'd keep the ratio of voltage over depletion width constant, which would mean you would have to adjust your doping in some way. And in the voltage case, you would let the E field go higher while keeping your gate voltage the same. And that's sort of easier to manage in terms of power supplies and design rules for your chips. Okay, so let's look at some of the physical effects that arise when you start making these distances smaller. Okay, so the first two kinds of effects we're going to consider come from either the short channel or narrow channel effects. So in both cases, usually we've been looking sort of sideways at the MOSFET. Here's our channel with length L, our drain and source. And what we haven't really talked about much is that this MOSFET structure actually goes back into the board too, and it has a certain width. So here's our two dimensions. So the narrow channel effects have to do with the W direction, and the short channel effects have to do with the L direction. When you look at this structure, you have to remember that this is a P-type semiconductor with an N-type channel, and both the source and the drain are N+. So they're in contact with this P material, which means that there's a PN junction formed around each one. And if we had no bias on the gate, we would actually see these depletion widths encroaching into the channel length. So this is the WD associated with the source. This is the WD associated with the drain. So really, in terms of the distance an injected electron would have to travel, it's not the physical dimension L between the metallurgical junctions between the N plus and P. It's this distance between the depletion widths. So instead, we would consider this L prime length, which would be L minus the depletion width on one side at the source minus the WD at the drain. So how do we deal with this? Now we put on a bias on our gate here, and I'm going to move the diagram over here and just draw the outline of the depletion width superimposed on a physical drawing here. So here's our oxide, here's our drain, our source, and our gate metal is here. So a first approximation is strictly geometric. The actual depletion width might look something like this, where this entire region is depleted. Here's your P, here's the entire depletion width, N plus, N plus. And we want to know about how much volume of material the gate will control. So the easiest model to make is to sort of make a trapezoid and say, well, the gate controls this much of the total depletion width. The drain takes care of this part, and the source takes care of this part. So whereas before we were considering, in a long channel case, the gate to be controlling a rectangle of charge, now we call it a trapezoid. And when you work out that geometry, you can predict that there will be a shift in the threshold voltage for the MOSFET, which is E NA x dt. So the maximum depletion width at threshold over the capacitance of the oxide, and then times another factor that comes from the geometry, square root of 1, and then we need another factor here of, I'll put it here, Rj over L. And the critical distance here is this distance from the corner of the drain over to the edge of the depletion width. That's this Rj distance. So the geometry here, you can see, comes into this factor. Overall, though, what this means is that the threshold voltage is going to move in the negative direction. So as you start shrinking the channel length, you're making L smaller and smaller and smaller. The threshold voltage is actually going to be changing lower and lower and lower. In the narrow channel effects, we have to look at the shape of the depletion width underneath the gate contact. We look down from the top. The gate contact is going to be a rectangle with dimensions L by W. And because of, for the same reason here, the actual depletion width under the gate is going to be sort of shaped more like a rounded rectangle as viewed from the top. It's a little bit bigger than the physical gate. And then if we view it from the side along, and we're going to cut along the width direction, it'll be shaped something like this. So your actual physical gate viewed from the side looks like this. But the depletion width extends this distance, R, excuse me, that shouldn't be a J. This distance R around from each edge. So again, making some arguments about the total amount of charge that the gate can control as a function of shrinking this width direction, you end up with an expression that the change in the threshold is now going to move in the opposite direction. It will be a positive shift. X dt is the normal distance to the gate. divided by the oxide capacitance, and then times what turns out to be sort of a fudge factor. We know that it scales with x dt over w, and we throw in sort of a fudge factor that's accounting for the geometry here. So this fudge factor will range between 0 and 1. We can summarize these two effects in terms of plotting the threshold voltage versus the length of the channel. Okay, so let's graphically summarize now what we just talked about for these threshold shifts. So on the x-axis, we're either going to have the width or the length of the MOSFET, and then we're going to plot the V threshold on this axis. So the short channel effects, remember, were a negative deviation from threshold. So this is short channel effects, and then the narrow effects shift you in the other direction. So one consequence is that if you shrink both the L and W at the same rate, they sort of tend to cancel. And you won't change your threshold voltage as much as you thought you would if you scale the total area instead of just the length or the width independently. So that's a nice thing, especially when we're talking about the motivation for scaling in the first place, which is to put more MOSFETs on the same area silicon wafer. So the area scaling sort of cancels out each other and gives you a relatively constant threshold voltage. So in this short little section, we talked about the motivations for scaling MOSFETs smaller, and some of the consequences in terms of the geometrical changes on the main control parameter of the MOSFET, the threshold voltage here. And we learned that if you scale the physical dimensions, length and width, at the same rate, these effects tend to cancel, although the cancellation is not perfect. You will have some shifting in the threshold voltage. But if you shrink both length and width together, the effects tend to cancel each other out. So we've learned something about the motivations for scaling, and now we'll learn in the next section about a few other consequences which are sort of side effects of this scaling.